of geometry and analysis, and they have to do mostly with the heat equation on a manifold. So I will start with describing a little bit what is the plan of my lectures, and then I will move on to first discussing in some detail the Riemannian situation. And then in the second part of the lectures I will also discuss the case in which one can move on to at least some interesting and large classes of sub-Riemannian manifolds. Okay, so the story starts quite a few years ago with a fundamental result of Italy and Li-Yau. This is 1986, and the paper is in Acta Mathematica. In this paper, they proved some fundamental a priori gradient estimates for solutions of the heat equation. And so let me discuss a little bit this setup. So, in order to motivate a little bit what I'm going to discuss, let me start with a basic, very trivial example in which the manifold is standard Rn. And let's take U to be the standard kernel. Here, of course, x is in Rn, t is strictly greater than 0. So we know that this is a positive solution of the heat equation. And if we take the so-called entropy associated with this special solution, so that's by definition is the logarithm of u. So we get minus n over 2 log of 4 pi t minus x squared over 4t. So that is the entropy, and then you can do a very almost trivial calculation by hands. You can compute the gradient of f, which is of course just minus x over 2t, and then let's compute also the time derivative of f, which is minus n over 2t plus x squared over 4t squared. And then you just observe, which is, I guess, that what Li and Yau did originally. You observe that if you combine these two quantities, so if you combine these two quantities, we will get x squared over 4t squared here minus x squared over 4t squared from here plus n over 2t. You just get that this combination is identically equal to this quantity here. Now this is a truly remarkable observation. As you see, I mean, it seems like this is invented in a way. I mean, I'm coming up with this quantity, but I will explain later on what is the meaning of this, in this case, identity. What is a deep result of Li and Yau? So Li and Yau proved, and this is just a special case of the general inequality, is that if you take M to be a complete non-compact n-dimensional Riemannian manifold with Ricci tensor bigger than or equal than 0, then if U is a positive solution of the heat equation on M cross 0 infinity. And if F is the entropy associated with that positive solution, then the entropy satisfies this inequality here. So notice that we have lost the identity that we had in flat Rn, but now we have an inequality here. Okay? And as you will see, this inequality goes in the correct direction for the applications that come from this inequality. So this is a very deep result of Li-Yau. And notice that it connects the heat equation to a global curvature assumption of the manifold, Ricci bigger than or equal than 0. So this was a circular ideas which had already been taken up by Yau in a series of papers that started in 1975. For instance, in 1975, Yau proved for the first time that under the same assumptions that you have here, there is a Li-Yau theorem which is exactly the same as in Rn. In other words, if you have a positive solution of Laplace's equation, there must be constant. So if you have a one-sided bounded solution of Laplace's equation, then it must be a constant. Under this assumption here. So Yau was the first one to connect in a very important way curvature assumptions on the manifold with global properties of solution of the Laplace Beltrami operator on the manifold itself. And this inequality of Li-Yau somehow, if you look at the work of Yau, the original work of Yau, you see that there is a strong connection between this inequality and the original work of Yau. So this was a circle of idea that was going around. Yau was the first one who started it, and then Peter Lee, who was a student of Yau originally, came into the picture, and they developed this whole theory. I want to emphasize that this is only a special case of the Li-Yau inequality. Li-Yau inequality has also the situation. Oh, I did not say here that the manifold is boundaryless. So I'm assuming here that the boundary of the manifold is empty. That's important. Otherwise, the inequality gets more complicated. And you need to make assumptions, curvature assumptions on the boundary as well to keep this inequality. And I also did not say anything concerning the case in which Ricci is bigger than or equal to, say, than minus kappa squared, where kappa squared is a bigger than or equal than 0 number. So there are lots of cases in the Li-Yau inequality, but I will mostly focus right now on this one, because as you will see, this contains already the essence of all the theory. All right, so my plan is to explain in some details what goes into this inequality here in the original proof of Li-Yau, and then also present an alternative proof to the original proof of Li-Yau, not just for the sake of presenting an alternative proof, but because I will emphasize some of the key points of the Li-Yau method, and I will tell you what are the points that do work when you move from the Riemannian to the sub-Riemannian case, and what are the points that instead encounter serious difficulties. And therefore the spirit of the alternative method is to overcome the addition of difficulties and try to view this inequality from a different perspective that better lends itself to generalizations to the sub-Riemannian case. Okay? So this is a little bit, the aim of my course, and I will now start by discussing a little bit in detail this inequality of Li-Yau. And of course, please do stop me if you have questions. I cannot promise that I will answer in Russian. My Russian does not exist, so I apologize for not speaking Russian, but I must say that when I was 18, I tried learning this beautiful language very hard, but I'm too old now, I've forgotten everything. So, I can only remember very few words. All right. So, let me start by some preliminary stuff. So first of all, let me show you what is the true inequality of Li and Yau, from which they immediately deduced this one. So let me, this theorem again is a theorem of Li and Yau. And it says the following. So let n be a complete, or completeness here is very important, it's a crucial topological assumption. If you remove it, everything breaks down. So this is a basic assumption that you have to have always. Let them be a complete, non-compact Riemannian manifold. N-dimensional. Or here, maybe I did say n-dimensional, so this n represents the dimension of the manifold. N-dimensional manifold. Boundaryless also. And suppose that U is a positive solution of the heat equation in n plus 0 infinity. Let Ricci be bigger than or equal than 0. I will recall, in a little while, I will recall a few preliminaries from geometry. So I will recall what the Ricci tensor is. Then there exists a universal constant. When I say universal, I mean that the constant depends only on bounds, on the dimension of the manifold, and on bounds from below on the Ricci tensor. In this case, the bound from below is 0. So, and there exists a universal constant, Cn bigger than 0, such that for any r bigger than 0, so if dr is the geodesic ball centered at some point, which I will call O of M, then the supremum of gradient U squared over U squared minus alpha ut over U, supremum over dr, is controlled by Cn times alpha to the 4 divided by alpha squared minus 1 times r squared plus alpha squared n over 2t. This for any alpha bigger than 1. And of course for any t bigger than 0. So the picture is this. I have the manifold down here. This is time. So I take any ball dr on the geodesic ball centered at any point, and then the supremum in that ball of this particular combination, here, particular nonlinear combination, is controlled by this dimensional constant times alpha to the 4 divided by alpha squared minus 1 r squared plus alpha squared n over 2t.
What is the denominator? Again, alpha. Oh.
Here? Yeah, alpha squared. So let me show you how, from this result, we immediately get this result here.
When you go to infinity.
We don't let t go to infinity here. T is a positive number which is fixed. Okay?
Excuse me, in the denominator, the
Here?
denominator, u squared or n squared?
U squared. I apologize for my bad writing. And maybe this is confusing here, so let me put the t-axis here. So it is just a dimensional constant. So let me show you how this theorem here so I can read all this stuff here. So let me show how the theorem implies the Li-Yau inequality star. I will call star this inequality here. Okay? Well, we have a complete non-compact Riemannian manifold. So I can take in this manifold the geodesic ball of radius arbitrarily large. So take any R and apply the theorem on the R. So we have that inequality over there. Now, you see, in this theorem, I have 1 over r squared here. This is the enemy. Okay? So, but I have 1 over r squared. I can take r arbitrarily large, so let's let r go to infinity. If we let r go to infinity, this object disappears. So this is gone from the picture.
The inequality is a little bit strange. It's like if we increase the value of r, the supremum is going to become larger, but the right hand side is going to be smaller.
You know, a priori, I don't know anything about this thing. This supremum could be positive, could be negative. It's what it is. Okay? So let the r go to infinity. We get the supremum of this quantity on the whole manifold is controlled by alpha squared over n2t. So at that point, so that means that letting r go to infinity, we obtain on m Cartesian 0 infinity gradient u squared over u squared minus alpha ut over u less than or equal than alpha squared n over 2t. And this is true for any alpha bigger than 1. Okay? Now let alpha go to 1. And we get this thing. Remember, this is going to be the gradient of the logarithm of u. This is going to be the length squared of the gradient of the logarithm of u. This is going to be the derivative of the logarithm of u. So we get this inequality here. We're finished. Okay? So this is the end of it. So now let alpha go to 1 to obtain star. And that's the end of it. So you see that the main essence of the theorem on Li and Yau is in this inequality here. This inequality is a stronger version of that one over there. All right, so so then in order to prove the theorem of Li-Yau, now we have to prove this theorem here. So let me then turn to some preliminary analysis that will lead us to the proof of this theorem. Well, before I start discussing, you know, how one goes, I mean, the original proof of Li-Yau for this inequality here, I would like to say a few words of why one is interested in this inequality here. And so, we all know a fundamental inequality which is true for the standard Laplace's equation, and it's the so-called Harnack inequality. So Harnack's inequality says the following. Suppose you have a harmonic function. I'm talking about a standard positive harmonic function in a ball of radius, let's say 4r. So in B 4r. Then the Harnack inequality says that the supremum of u in Br is controlled by a universal constant times the infimum of u in the same ball. And this inequality of Harnack plays a fundamental role in the analysis of partial differential equations or elliptic partial differential equations of order 2. Okay? So you have to stay inside, and you have to stay inside by a proportion which is fixed. In other words, the quotient between this radius and this radius must be an absolute number. If you change the proportions, then the constant may blow up. As this ball goes to the bigger ball, then this constant will blow up. Okay, so you have to stay strictly inside. But this fundamental result of Harnack is, implies immediately a absolute, universal. By universal, I mean that it depends only on this number. A universal alpha modulus of Hilbert continuity. In fact, I mean, it's easily seen that this modulus of continuity depends directly on this number here by a standard argument that I will not present. It's a fairly standard argument. So you take a ball of radius r, and you look at the supremum of u minus u. That's a non-negative harmonic function. And then you look at u minus the infimum of u, that's a non-negative harmonic function. You apply this inequality to both this function, you subtract supremum minus infimum, then you get an estimate of the oscillation, and you see that the oscillation going from a ball of radius 2 to a ball of radius 1 decreases by a factor which you can control directly in terms of this constant here, and that's Hilbert continuity. Okay? So why is this Harnack inequality important? Because it implies, one of the things that it implies is Hilbert continuity. And that was the main breakthrough in 1957, which was due to Ennio De Giorgi, to show that this inequality continues to be valid for, and the ensuing delta continuity continues to be valid for solutions of divergence form equation with just elliptic divergence form equation with just bounded measurable coefficient. That allowed the Giorgi to solve Hilbert's 19th problem, which was a very fundamental open question at that time. So, why am I talking about the Harnack inequality in connection with the Li-Yau inequality? It seems like these two things are completely unrelated. Well, the reason for which I'm discussing this inequality is that this inequality, which is written here, the inequality of Li-Yau, imply in a very standard fashion a scale invariant Harnack inequality on manifolds. So let me tell you what it. So I will come back to this thing. Right now, I'm just, talking around that inequality and giving you a little bit of motivation, telling you a little bit why Li and Yau were so interested in this inequality here. Okay. So this result of the Harnack inequality goes back to 1887. I don't remember Hassel. Harnack proved it, I think, in 1887, something like that. And of course, one would wish to have a similar inequality for the heat equation, but for the heat equation, things are not so easy. It is true, the Harnack inequality is true, and I will give you now, I will move on to the parabolic setting. So just think of this as a cylinder. So down here there is Rn, and here there is T. So think of a cylinder which has base, a ball of radius proportional to R, and which has height along the t-axis proportional to r squared. Why r squared? Because I'm looking at the heat equation. And the natural geometry for the heat equation is not the homogeneous geometry of the Laplacian, because we have two derivatives here and one derivative here. So the natural geometry for the heat equation is based on these dilations here. Lambda x, lambda squared t. So if you keep in mind those dilations, then the geometry becomes r squared. Okay, this is the time direction. So the Harnack inequality for the heat equation says the following. Suppose we have a positive solution of the heat equation in a cylinder like this, and now I will take sub-cylinders, and I will call this, so this will be my big cylinder QR. I will call this Q minus R, and this one Q plus R, and maybe this I should call it by consistency, I should call it Q4R. So keep in mind that thing there. So there is a big ball of radius 4R here. Here there is a ball of radius R. Again, this is a ball of radius R. And then there is a time lag proportional to R squared here, here. And these distances are proportional to R squared. So everything is kept proportional. Otherwise, the inequality is not true. So then the Harnack inequality for the heat equation was proved in 1955 independently by Bruno Pini and Jacques Hadamard. They proved it independently, one from the other. The two papers appeared almost simultaneously. And the Harnack inequality says that if you have a positive solution of the heat equation in this big cylinder, then the supremum of u in QR minus is controlled by a dimensional constant times the infimum of u in QR plus. Okay? Notice two things. I have to stay away from the initial time, t equal to 0. As you get closer and closer, even if proportional to r squared, closer and closer to the initial time, this constant blows up. So you cannot get to time t equal to 0. You have to stay away. You have to let time go by in order, because of the infinite speed of propagation of the heat equation. That's why. So there is a gap, and there is a gap here. So in other words, you cannot control supremum and infimum at the same time level. You have to have a gap in time for the heat equation. So these are two natural obstructions for the heat equation, and you can produce very simple counterexamples to the inequalities that I was talking about, which are not true, by working with translated of the fundamental solution, the Gauss kernel that I wrote before. So there is this scale invariant Harnack inequality, which for the heat equation was proved in 1955 by Pinion and Amar. Well, what Li and Yau were after was a generalization of this inequality to the case of complete manifolds with Ricci bounded from below. And the reason for which this inequality becomes really important is that I will show you this. So I will Anastasia. I caught you. She was falling asleep already. It's okay. It's completely okay. The important thing is that I don't fall asleep, otherwise that's a problem. So, let's see. So, so let me still call this. So, observation. And I will prove this observation. It's not completely trivial, but it is fairly standard by now. Okay? So the Li-Yau inequality star implies the following theorem. And I will call this scale invariant Harnack inequality. So in this theorem, the assumptions on M are the same for the validity of star. So I will not write them again. M is otherwise Anastasia will fall asleep immediately. So the manifold is complete, is non-compact. It's an n-dimensional manifold with empty boundary, and with Ricci bigger than or equal than 0. So Ricci bigger than or equal than 0 is important, otherwise this inequality is not true as I've written. There are additional terms which I will discuss later. Okay? So if U is a positive solution, so okay. So it's a 45. Okay. It's a solution of heat equation in M cross 0 infinity. Then for any x, y in M, and for any 0 less than s, less than t, less than infinity, one has U at xs. Notice that s is a time which comes earlier than t. So this is less than or equal than u of yt times t over s to the n over 2 times the exponential of the distance between x and y squared divided by 4 t minus s. So this is a fundamental theorem of Li and Yau, again, that they deduced from this inequality here. Okay. And this is a scale invariant Harnack inequality. Why? Here, this dx and y is the geodesic distance on the manifold between x and y. Okay? So, take for instance this geometry that I was telling you before. So, take dxy less than or equal than r, and t minus s equal to a constant, so let's call it c, times r squared. In order to respect this geometry. So I'm taking x and y in a bulk of radius r, let's say, and there is a, so here there is xs, here there is yt. I'm taking t minus s to be a multiple of r squared. All right, so see what this inequality gives you.
Do we need the minus?
No,
Or no?
absolutely no. It's a plus. You're thinking about the fundamental solution if it has a minus, no? But here in the Harnack inequality there is a plus. So if dx and y is less than or equal, say, than constant times r squared, then this quantity is controlled from above by c times r squared. This quantity here is other constant times r squared. So r squared cancels and you get an absolute number here, a universal constant. Okay? T over s. Oh, by the way, t and s, you have to respect this geometry. So s is proportional to r squared and t is also proportional to r squared. So this quantity here becomes a universal number. Okay? And what you get is that u in excess is less than or equal than a universal constant times u or yt. Okay? So you get the generalization of the Harnack inequality to Riemannian manifolds. Now, of course, I have to show you how the Li-Yau inequality implies this, and I will do this in detail. I will give you the argument of Li-Yau to establish this. Incidentally, this inequality here has to do with, since this is the laboratory geometric control theory, this has to do with control theory. This is an inequality which to people in control theory is well known. I mean, they understand this inequality in a different context. So I will also discuss this aspect a little bit later on. But at this moment, I just wanted to make a remark that once you have this inequality, then by fairly standard arguments, you can prove the scale invariant Harnack inequality. Wow, that's a very big result. Once that Li-Yau had this result, then there is a machinery, a very important but very well developed machinery that says, well, if I have a scale invariant Harnack inequality, then I can prove upper Gaussian bounds for the heat current. And this is another result that Li-Yau were after. So, so let me make this observation, because I mean it's important to a little bit understand what is the motivation behind this, because when you look at that, it's okay, that's a very beautiful inequality, but what do we do with it? The reason for which they proved this inequality is because they wanted to prove this result. That's one of the primary reasons that they wanted to achieve. They wanted to show the scale invariant Harnack inequality. Once you have the scale invariant Harnack inequality, then a world of possibility opens up. And then you can get off diagonal Gaussian upper bounds. I want to emphasize that I'm talking about upper bounds. I will talk about off diagonal lower bounds, and that's a different issue. Is it your phone or my phone? I think it's, is it your phone? Probably. Are you trying to tell me that I'm speaking too much? I don't know if it is yours or mine, but let me shut it. Okay. So off diagonal Gaussian upper bound is, I will denote with P, X, Y, T, the T kernel on M Cartesian 0 infinity. So this is the fundamental solution of the heat equation with singularity at x equal y. The heat equation is a symmetric, is the generator of a symmetric semigroup on the manifold. So pxyt is equal to pyxt, and it represents the solution of the Cauchy problem. So if you look at the Cauchy, so if you look at ptf x equals the integral over m of px y t f y dm d mu y, so this is the Riemannian volume on m. Then this object here defines a one-parameter semigroup of operators, of contraction operators, and this function here in particular is under suitable hypothesis on F, is the unique solution to the Cauchy problem for the heat equation on M. So this is you can prove by functional analysis that this is strictly positive at every x, y, and t bigger than 0. And what one can show is the following, that the scale invariant Harnack inequality implies the following estimate: Pxyt less than or equal constant times the volume of the ball. This is the volume of the geodesic ball centered at x with radius square root t times x minus of dxy squared divided by 4. Let me put here 4 plus epsilon. So this constant depends also on epsilon times t. So you can show that for every epsilon bigger than 0, this estimate holds globally on the manifold, with a constant which depends on the dimension of the manifold and on epsilon. Again, I'm assuming Ricci bigger than or equal than 0, otherwise this estimate is not true the way I'm writing it. And the constant blows up as epsilon goes to 0. So this is, you were referring to the minus, here you get the minus.
4 plus epsilon.
4 plus epsilon. So you can prove that for every epsilon bigger than 0, there exists a constant c depending on n and epsilon, such that this inequality holds. Now notice that in the case in which you are in flat Rn, this is t to the n over 2. The volume of the ball centered at any point x with radius square root t is t to the n over 2, and you get back the classical result that we know. Okay, you get the fundamental solution of the heat equation. All right, so this is called off-diagonal Gaussian upper bounds because x and y are allowed to be everywhere on the manifold, not just x equal to y. Okay, so getting this estimate takes a certain amount of work, and I will probably will have time to discuss this a little bit. But this estimate here comes from this theorem here. Okay, and then you can combine this estimate with that theorem and with another estimate which has to do with the volume of the geodesic ball and get a lower estimate for the fundamental solution. So then you get complete picture for the fundamental solution in terms of Gaussian bounds. You get a different constant, but this is another story which I will discuss later on. So I will stop right now and make a little break. And you have the widest example of manifolds with Ricci bigger than or equal than 0. Yeah.
Is this the precise result?
No, it's not
But
the precise
any
result.
manifold such a metric exists.
What I'm saying is that if you allow bigger than or equal than 0, then the topological restrictions on the manifold become very vague. There are no special topological restrictions. That's what I'm saying. I mean, you asked me if there is a connection between Ricci and topology, and I told you, if you know that Ricci is positive, then there is this fundamental result.
Let me ask more precisely. Is it true that on any manifold there exists a complete Riemannian metric with non-negative Ricci curvature?
You mean on any non-compact manifold?
On any non-compact manifold. Most probably it is open.
This is not, I don't know the answer to this question, and I don't think it's so easy to answer this question. Yeah. 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 So, let me go back then to, some preliminary discussion which will lead us to the proof of this inequality here. So, there are two main ingredients. So, two main ingredients which go in the proof of the Li-Yau inequality. Okay? The first one is a fundamental identity which is due to Solomon-Bochner. So Bochner identity this identity not only holds for functions, I will write it for functions, but it does also hold for differential forms, and in that case it's called the Bochner-Weizenburg formula. Okay, so let's suppose we take a function of class C3, M. M is just a Riemannian manifold, no completeness assumption, just any Riemannian manifold. Okay? Then, if we take the Laplacian, this formula is beautiful because in this formula you see for the first time the interplay between a differential operator on the manifold, the Laplace of the prime operator, and the Ricci tensor. I will write the formula. So, Laplacian of the length of the gradient of f squared. The gradient of f is a infinity function, is a vector field on the manifold. Okay. So this is equal to twice the square of the Hilbert-Schmidt norm of the Hessian of f. So by this I will denote the Hessian of f. Okay, which in a local coordinate system is okay. And plus twice plus twice Ricci of gradient f, gradient f. So this is the Bochner formula. In the case of a flat Rn of Ricci bigger than or equal than 0, this formula tells you that if you take a harmonic function, then the length of the gradient of a harmonic function is a sub-harmonic function. I'm saying Ricci bigger than or equal than 0, f harmonic. F harmonic, this guy is gone. Laplacian of f is 0. This is bigger than or equal than 0. because Ricci is bigger than or equal than 0 by assumption. And then this tells you that the Laplacian of this function is bigger than or equal than 0. Okay? So, and that's the way Solomon Lochner used this formula to get information on eigenfunction on Laplace-Beltrami operator on compact manifolds. So this is the Lochner formula. And the second important result that goes into the proof of the theorem is the following Laplacian comparison theorem. So the Laplacian comparison theorem is a beautiful theorem that goes under the name of the comparison theorems in Riemannian geometry. And this theorem says the following. Suppose we have a manifold M, which is complete. Here, completeness is important. So here, no assumption whatsoever, just Riemannian manifold. So here, complete Riemannian manifold. Such that Ricci is bigger than or equal than minus n minus 1 times kappa squared. N minus 1 is just symbolic. We can take it, but because with this thing, it's a normalization factor. So, but the important thing is this kappa squared. Here, kappa is a real number. So I have a complete Riemannian manifold with Ricci bigger than or equal than minus n minus 1 kappa squared. Kappa can be 0, of course, in which case this is just Ricci bigger than or equal than 0. So let n be the simply connected model space with sectional curvature with constant sectional curvature kappa squared minus kappa squared. I'm a little bit worried because if I write this kappa squared, then maybe I'd have to remove the square. Let me see, because I want to include also the case of negative curvature. Well, I do include the case of negative curvature, of course. But then, how do I include the case of positive curvature? I want to remove this thing. Let me remove this, okay? Let me write it just like this. With constant sectional curvature equal minus kappa. So let me use that blackboard to continue. So let Rm x and Rn y denote geodesic distances on M and N from fixed points. Okay? So let x be a point in M be such that Rm is differentiable at x. This means that x is not a point of the cut locus of the base point. So notice I'm taking distance from a fixed point on M. The cut locus is the point where the exponential map ends to be a local diffeomorphism.
Excuse me, Rn is the distance from fixed point x to some
let me draw a picture. So
of either
I draw a picture, you will see. So some point O. X is distance from some point O.
Okay.
Then I have model M here, let's call it O prime, and then I have point Y. Okay? So I'm assuming that X is a point at which Rn is differentiable, which means that I'm staying outside of the cut locus of O. If I hit the cut locus of O, then this function ceases to be differentiable, okay? So, and let Y be a point in N such that, let me keep this in the file, be such that Rmx is equal to Rmy. Then, and that's the conclusion of the theorem, the Laplacian in M of Rmx is less than or equal than the Laplacian in N of Rmy. That's what the Laplacian comparison theorem says. It's a fundamental tool in Riemannian geometry. And it enters, in the program of Li-Yau, it enters in a crucial way in the proof of this inequality.
But, excuse me, then maybe k must be positive. You write that k is arbitrary real number, so it's strange a bit.
Okay, you're right. Let me restart. You're absolutely right. Here we go again. So this is fine now. Okay? There must have been a reason for which I was writing this k squared at the beginning. You're absolutely right.
Can you give any reference?
The Laplacian comparison theorem. There is a yes, there is a classical book by Chavel, Isaac Chavel, in which this theorem is proved.
What is connection between M and N? M and N?
Did I say, here it is. N is the simply connected model space with constant sectional curvature minus kappa squared. Okay? So, for M, there is only a bound from below for Ricci. Here, I'm taking... Okay, let me show you an immediate corollary of this. Corollary. Where can I go? Corollary. Well, it's time to get rid of this. I'll come back to this one. I will rewrite it again. I wanted to keep it on the blackboard because... So... Suppose Ricci is bigger than or equal than 0, okay? Which is the case of the inequality which I just erased, the Li-Yau inequality. Then, outside of the cut locus of O, the Laplacian comparison theorem tells us that the Laplacian of the geodesic distance is less than or equal to n minus 1 over Rmx. Let's see why. Okay. It's a very simple fact. So proof. assuming that kappa is 0 now. I'm assuming that kappa is 0. So n, the simply connected model with constant sectional curvature 0 is Rn, is flat Rn. So kappa is equal to 0 implies that n equals Rn. And therefore, Rn of y is simply our good old friend, the Euclidean distance. Okay? And we all know that if we take the Laplacian in Rn of the Euclidean distance, this is equal, outside of the origin, is equal to this. Okay? However, the theorem, the hypothesis of the theorem, x is a point at which the distance from x to O is equal to the distance from y to O prime. So this guy here is equal to n minus 1 over Rm x, by my choice of x. And then from here, and from this, we immediately get this statement here. Okay? So when reach is bigger than or equal than 0, the Laplacian of the geodesic distance outside of the cut locus of the base point satisfies this inequality pointwise, and moreover this inequality is also true in the sense of distribution on the whole manifold. So this also holds not only but in d prime of m holds globally. This was a result that was proved by an Italian mathematician much earlier. So we have this inequality outside of the cut locus, and we have the same inequality in the sense of distribution of the whole manifold. All right, so that's a Laplacian comparison theorem. Now,
excuse me?
yes.
I'm sure how inequality can be understood in this distribution sense.
It's a differential operator.
Yes.
So
yes.
multiply by a test function, put the Laplacian on the test function.
Yeah, it is some distribution, I understand.
Yeah.
But there is no inequalities between distributions.
In the sense of distribution, there is inequality because test functions are supposed to have a sign when you talk about inequalities in the sense of distribution. So you don't just work with any test function. When you want to, it's like when you want to define a subharmonic. When you want to find subharmonicity in the sense of distribution, you take test functions with a sign, and that's the same.
Distribution is non-negative if
distribution is non-negative for any test function which is non-negative.
Yeah.
Then inequality holds.
Now I see.
Okay. Any other questions? Okay, so let's keep in mind this corollary, because it will play an important role for us. So this is the boxed part, is the part that will be important for us later on in the proof of the Li-Yau inequality. So two things you have to keep in mind. The Bochner identity, or the Bochner identity follows quite immediately from the Ricci first commutation identity.
It is just a local formula.
Bochner identity is a local formula. I mean, it just expresses the fact that when you are on a manifold, if you start taking 3 derivatives, then you get curvature. Notice I'm taking 3 derivatives. There is 1 derivative here, and there is 2 derivatives here. So Ricci first commutation identity tells you this. If you take a Laplacian, f is a function of class C3. I'm taking everything here, I'm taking the ith projection of the gradient of f. The gradient is a vector field, so in a local coordinate system I'm projecting it on a local basis. Then this is equal to this plus this. And Rij, this is the Ricci tensor. So if you apply this formula, this identity, to this thing here, you just write, I mean, you follow your nose here, you write and then you use the fact that the Laplacian of the square of a function is 2g Laplacian g plus 2 raised to the square. So this becomes 2 sum I from 1 to n. Laplacian of this. Okay? And then I have, so this takes into account this, and then I have plus 2 sum I from 1 to n. And then I have sum j from, so let me put everything here, I and j from 1 to n. Okay, so this term here is this. Okay? In this term here, you apply Ricci commutation identity, and you get this guy here after you commute, and then you get this guy here. Rij gradient IF nabla JF. It's exactly this. So it follows from this identity immediately, the Bachman's formula. But it's a remarkable formula. Okay. So that's a proof of Bachman's formula. If you want to see proof of the Laplacian comparison theorem, then I mean you can look up in books because that's quite involved. It uses Jacobi fields, and so a good reference is the book by Chavert, Riemannian geometry, or the book by Pedersen, Riemannian manifolds. Okay, so. Anyhow, so okay, so now we have these two tools here. So
is this your spelling right? Probably Peterson.
yeah, it's Pedersen maybe. Let's see, is
Probably
I'm not sure. I'm not
Yes,
sure.
Pedersen is very old Norwegian geometry. This is American.
No, he's at University of California in Los Angeles. This guy. So
It's pupil of Carsten Brock.
yeah, is better than. Okay. All right. So
actually, they both are not authors. Who was first? Do you know?
Oh, I don't know who was the first one to prove it. There is this book by Comparison Theorems in Riemannian Geometry. But I don't know, it's in geometers don't say who is. I'm not a geometer, so I'm the last.
By Chigger, yeah?
Yeah, but there is a book by.
It's a very recent book.
There is a Chigger and Ebbin comparison theorems in Riemannian geometry. They have all these theorems, but I think that the theorem was around before them. He was before them. I don't know who proved it in this form, or who was the first person to prove it. Yeah. Okay, so
excuse me, one more question about this comparison theory. Actually, the question from Sergei. Does Rauch comparison theory works in the proof?
I'm sorry, that's the.
You mentioned that Jacobi fields.
Yeah.
I used. And probably Rauch comparison theory for Jacobi fields.
Rauch comparison theorem enters everywhere in this business. Yeah, everywhere.
No, the question was, what is connection between geometric comparison theorems
You got the answer right now.
and analytic comparison theorems?
Sturm-Liouville theory. I guess that's the Sturm-Liouville theory. I guess that's the connection in the end. Yeah. Okay, so well, let me start then with a lemma. So my objective now is we want to move toward toward the proof of Li-Yau theorem. The one that implies the Li-Yau inequality. So we have to do some work. So let me start with some preliminary facts. So let me take a positive solution of the heat equation. And let's take f to be the logarithm of u. Okay. So let me use the formula, the standard fact using the chain rule, that if you take the Laplacian of a composition, then you get h double prime u gradient u squared plus h prime u Laplacian u. So let me correct here. Well, no, that's fine. So let me take h of t to be the log of t. Then the Laplacian of f is the logarithm of u, according to this formula. So I get 1 over t here, I get minus 1 over t, so I get minus gradient u squared over u squared plus Laplacian u over u. Remember, I'm taking a positive solution, so I can divide by u. There is no problem. Okay? So if I take the heat equation on F, what do I get? Since Ft would be equal ut over u, I get the heat equation on u divided by u, so I get heat equation of u divided by u minus the gradient of u squared divided by u squared, that's like the length squared of the gradient of f. F, remember, is the logarithm of u. Okay, so this is just calculations. You have to believe that. I'm taking u to be the solution of the heat equation, so this equation simplifies, and we get just this. Okay, so this is just a preliminary observation. So let me write it somewhere. Let me write it here. I guess I can erase this intermediate step. I can erase this. And so if f is log u, and u satisfies the heat equation, then f satisfies the equation gradient f, Laplacian f minus ft equal minus length of the gradient of f squared. Okay, so let's keep this equation in mind because I will be using it now. So, and now there is a first lemma. Can I erase here? Okay. Lemma. As you will see, this lemma will only be a consequence of some clever calculation and Bochner's identity. So there is no comparison theorem in this lemma. Okay? So lemma, for any alpha bigger than or equal to 1, let capital F be equal to t times. But this lemma is due to Li-Yau, of course, it's not mine. I'm telling you Li-Yau story right now. So t times gradient f squared minus alpha ft. Then Laplacian f minus ft is bigger than or equal than 2t over n times gradient f squared minus ft, everything squared, minus 2 gradient little f, gradient capital F, minus maybe, just let me write. Capital F over t. I'm assuming that t is bigger than 0, so I can write it like that. Okay? So I'm going to prove for you this little lemma here. As you will see, this lemma seems that it comes out of the blue. It's some clever lemma that they cooked up because they need it somewhere later on, but you will see it's not completely out of the blue. Why? Because remember the function in the theorem. So let me go back for a second. I'm going to erase at least this top portion here. I will keep the Bochner's formula down here because I'm going to be using it. Remember the theorem that we want to prove. The theorem says that the supremum in VR of gradient f squared minus alpha ft is less than or equal Cn dot dot dot. Okay? Alpha to the 4th divided by alpha squared minus 1 times r squared plus alpha times n over 2t. That's the blah blah blah. The blah 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 is this. Is alpha to the 4th divided by alpha squared minus 1 r squared plus alpha n over 2t. That's the theorem that we want to prove. Look at this quantity here. This quantity here is capital F divided by t. Okay? So this theorem is telling me something about the heat operator applied to capital F. The idea here to prove this thing is to apply the maximum principle. So when you want to apply the maximum principle using calculus, you have to be able to estimate the heat equation acting on the function. And this is why this lemma is important. This lemma is only one piece of the puzzle. As you will see, there is another piece of the puzzle, which is the Laplacian comparison theorem. But this is why this comes into play. I am telling you this lemma, it seems that it comes out of the blue, but if you put the pieces together, after I tell you the whole picture, you will see that this has a logic. It's a very important logic. All right.